Starting chapter 4 on the chain rule. So we start with an idea. If we consider the function f of x is equal to 4x cubed plus 1, if we were to expand that, it would be 16x to the 6th plus 8x cubed plus 1. Not terribly difficult. And if we take the derivative of the expanded form, we get 96x to the 5th plus 24x squared. But if you said, well, this 4x cubed plus 1 is being raised to a power of 2, can I use the power rule? The answer is no, but it's interesting as to why not. If we just apply the power rule to the 4x cubed plus 1 squared, we get 2 times 4x cubed plus 1 raised to the first power, which is equal to 8x cubed plus 2. Now, if you compare that to what the actual derivative should be, I want you to notice something. I'm going to go up here to the f prime of x. If I were to factor out a 12x squared, it would be 12x squared times 8x cubed plus 2. It's off by a factor of 12x squared. Now, the question that I have for you is, where in this expression could we get a 12x squared? What operation could we do with any part of this where we could get a 12x squared? So, what is it?
The derivative of 4x cubed.
Yeah, it's the derivative of the 4x cubed, isn't it? Because we would be multiplying the 4 times 3, and this would be x squared. And the derivative of the 1 would be 0. So we could get that by taking the derivative of the inner part. And this is the whole idea of the chain rule, which we will use quite a lot actually. The chain rule says that if f is differentiable at x of g and g is differentiable at x, then f of g of x is differentiable, and the derivative with respect to x of f of g of x is equal to f prime of g of x times g prime of x. In Leibniz notation, if y is a function of u and u is a function of g of x, then we can say dy dx is equal to dy du times du dx. We'll do an example like that in a moment. So basically, we're saying that if you have a composite function, remember a composite function means you have one function inside of another function. The derivative of that composite function is the derivative of the outer function. So here, the f prime, leaving the inner function alone, then multiply that times the derivative of the inside function. So the idea that almost everybody uses with this is it's like you're peeling something with multiple layers. You deal with the outside layer, leaving the inside layer alone, and then you take the next layer off. So let's find the derivative of y equals sine of 3x squared plus 5x with respect to x. So dy dx is going to be equal to, we start with the outside part with the sine. The derivative of sine is cosine, and we're going to leave that inside part. What older textbooks, and almost nobody uses this anymore, but I think more people should, it's called the argument. What are you taking the sign of? So we're going to leave the argument alone. And then we're going to multiply that times the derivative of the argument, the derivative of the inside part. So that'll be 6x plus 5. In most cases, if this is a multiple choice question, they're going to write that 6x plus 5 first. Again, so there's no confusion as to what the argument on the cosine is. And that's the chain rule. All right, let's go on to page 2. So an object moves along the x-axis so that at any time t greater than or equal to 0, its position is given by x of t is equal to cosine of t squared plus 1. Find the velocity of the object as a function of t. So the velocity of t, and you don't absolutely have to write this, but I just about always do, that v of t is equal to x prime of t. I let people know what I'm doing. So we'll take the derivative of the outer function, so it'll be negative sine of, the argument stays the same, t squared plus 1, times the derivative of the inside part, the derivative of the argument, which is 2t. So that'd be negative 2t sine of t squared plus 1. Our next example takes this a step further. So I want you to notice that although there's one set of parentheses, this is actually a triple composite, meaning it's a function inside a function inside another function, because we're taking the sine of 3t, and that's not just t. If it's anything other than just the variable, then the chain rule applies. So now my derivative, g prime of x, we'll start by taking the derivative of the outermost part. The derivative of tangent is secant squared. And we're going to leave the original argument alone, 5 minus sine of 3t. Now we'll take the derivative of the 5 minus sine of 3t. Well, the derivative of the 5 is 0. The derivative of negative sine of something is positive cosine, and we're going to leave that argument alone. We're going to leave that as 3t. And then we'll take the derivative of the last argument, 3t, which is 3. Again, in most cases, the constant gets moved out in front. So that's 3 secant squared of 5 minus sine 3t times the cosine of 3t. It's not always that the trig function is on the outside. I'm going to add another example in here just real quick. Let's find dy dx for y is equal to sine to the 5th x. What you have to remember is that sine to the 5th x is really sine of x raised to the fifth power. So here my outer function is the power and the inner function is the trig function. So dy dx is going to be equal to, using the power rule first this time, I'll have 5 times sine of x raised to the fourth times the derivative of sine of x, which is cosine of x. And then typically, since the original was written in this form where we didn't have parentheses, we would rewrite that as 5 sine to the fourth x times cosine of x. All right, did you guys do some things with parametric curves last year where you defined x as one function and y as a different function? I just don't know I don't know enough about the AP Pre-Cal curriculum to know if that's in there or not.
The word sounds familiar, but I don't remember.
Okay, so basically, I'm gonna give you a reference that is way too old for you guys, but have you ever heard of an Etch-a-Sketch? Okay, so it was a very popular toy in the United States, probably in the, oh gosh, probably started in the late 50s and was popular maybe even through the early 70s, but it's pretty old. But basically what it did is it had this screen and it had this little thing that would move across it and it would leave a line as it moved across. And you had a horizontal control and a vertical control, and you controlled them separately. So that's what parametric equations are like. One thing is controlling the horizontal, and something else entirely is controlling the vertical. That's the easiest way I think of to think of parametric curves. So when you have one here, x of t, y of t, it's differentiable if if x of t and y of t are differentiable and x prime of t is not equal to 0. And here's why. Because dy dt, using Leibniz notation, is equal to dy dx times dx dt. If we divide both sides by dx dt to solve for dy dx, we get dy dx is dy dt divided by dx dt. And you can think of it as, well, these dt's would cancel if they were actually numbers. That's not actually quite what's happening here, but it makes it easy to think about. So let's write an equation for the line tangent to x equals secant of t, y equals tangent of t, for t between negative pi over 2 and pi over 2 at t is equal to pi over 4. So anytime we want to write the equation for a tangent line, we need two things. We need to know what point it goes through, and we need the slope of the tangent line, which would be dy dx. So first I'm going to find the point. The x-coordinate will be secant at pi over 4. Secant is the reciprocal of cosine. So instead of square root of 2 over 2, this will be 2 over the square root of 2, which is itself the square root of 2. And then y is going to be tangent at pi over 4. And what is tangent at pi over 4? Uh-oh. Yeah, it's 1 because sine at pi over 4 is square root of 2 over 2, and cosine and of pi over 4 is square root of 2 over 2, and tangent is sine over cosine, so that's 1. So we've got our point. It's the square root of 2 comma 1. So dy dx is going to be dy dt, so the derivative of tangent is secant squared over dx dt, which will be the derivative of secant t, and that'll be secant t tangent t. Which we can simplify to be secant of t over tangent of t. So then our slope for the tangent is going to be secant at pi over 4 over tangent of pi over 4 which is, we already figured out both of those things, which is why I didn't simplify this any further, because we could have changed it all into terms of sine and cosine, and I frequently do. So the slope of the tangent line is just the square root of 2. So the equation of the tangent line is going to be y equals 1 plus the square root of 2 times x minus the square root of 2. And again, if in your book, they're going to change that into slope-intercept. This one in particular does simplify quite nicely, but on the AP exam, I would never spend the time, unless it was a multiple choice question. Right, they might have it in that form, although they're actually pretty good about just leaving it in point slope form. All right, let's see. A couple more examples. Find the slope of the line tangent to the curve y equals sine to the 5th x at x equals pi over 3. You know, I forgot this problem was in there. Otherwise, I wouldn't have done that earlier one. Well, let's go through it again. It doesn't hurt. So this is y is equal to sine of x raised to the 5th. So then dy dx is 5 sine of x raised to the 4th times the derivative of the inside part, cosine of x. So the slope of the tangent line is going to be 5 times sine of pi over 3 raised to the 4th times cosine of pi over 3. Sine at pi over 3 no. No. Cosine at pi over 3 is a half. Yeah, square root of 3 over 2. Raised to the 4th power times cosine at pi over 3 which is a half. So that's going to be half times 9 over 16 times a half, which is 45 over 32. All right. Last question. I don't think you'll see this particular terminology on the AP exam, but it does show up in some calculus textbooks. So again, I try to mostly spend our time on things that are going to be on the AP exam. But since you're likely to be going on to other math classes, you may see this. So this is saying take the derivative with respect to x of f of, and I forgot to write the g in here, g of x equals and evaluate that at x is equal to 0. Oh, by the way, I changed this one. The u is equal to x squared plus 3x plus 6. It avoids a major problem that we would have otherwise. Now, there are two different ways you can do this one. You can go ahead and substitute all of this in each of the u's and do it that way, which is fine. It's a little bit easier, in my opinion, if you don't. So if we take the derivative f prime of u and then multiply it times the derivative of u with respect to x, that gives me dy dx. So taking the derivative of f of u in terms of u, so I'm leaving that inside part alone. U is the inside part. So I'm going to have to use the quotient rule. So it'll be u minus 5 times the derivative of the numerator, which is 3u squared plus, just 3u squared minus the numerator, u cubed plus 3 times the derivative of the denominator, which is 1, divided by the denominator squared. And then I'm going to multiply that times, I'm going to take the derivative of u with respect to x. That would be, 2x plus 3. Now when I'm ready to evaluate this, what I'll do is find, well, what is u at 0? U at 0 is equal to 6, right? If I substitute in x is 0, I get 6. And I can now put that in for all of the u's. So I'm going to have 6 minus 5 times 3 times 6 squared minus 6 cubed plus 3 all over 1 squared times, when x is 0, that last expression in terms of x is going to be 3. So let's see, that's 36 times 3 is 108. Minus 6 cubed, I think that's 216, plus 3. Tony, you've got your calculator handy. Is 6 cubed 216? I just can't remember.
Yeah.
Okay, so this is minus 219 all over 1 times 3. So that's negative 111 times 3 is negative 333. And frankly, if that's a slope, you're going to have a difficult time telling that from a vertical line. Actually, once you get to, slopes that are bigger than 10, unless you have some frame of reference that helps you, it's really hard to tell them from a vertical line. And this is way bigger than that.
If u equals to 5, is this undefined?
Yes, this is because the function's not defined at 5, which is why I had to change this to a 6, because otherwise the function wasn't defined, the derivative wasn't defined. It all went to, if you'll excuse the phrase, it all went to hell in a handbasket. Any other questions?